All right, so we'll clean off our work on contaminant transport. We made the point that you had to forget everything about two fluids flowing at the same time, and we're talking only about one fluid moving and carrying stuff with it in dissolved form. We talked the last two events as the first one was talking about what the advection dispersion equation is. And so perhaps it might not be terrible to write it down. It's something that is change in concentration with time, I guess these are partials, is equal to longitudinal dispersion, change in concentration in the downstream direction, minus advective velocity, actually I'll write the other one first, plus transverse dispersion, change in concentration across the flow path, and minus the advective velocity dc dx. And you know the behaviors that we've been looking at. We've drawn this, you're way beyond this now, but we've always had these three-part response curves, and you know that this is the upstream boundary condition, I guess. This is our core, if you think of it that way. I should probably copy it from what we've done before. This is x, and this is the RTD curve as it comes out. So this is time, this is time, this is length, this is relative concentration in all of them. So this is 1. And these, I'm not sure what we used before. So this was advective velocity, or rather the location of the front. This is the location of the front. We know that velocity is equal to length over time, so time traveled is equal to velocity. This is, I guess, the only one we don't have. Length is equal to velocity times time. And we know that often this is the case for if longitudinal dispersion is not equal to 0 and longitudinal dispersion is equal to 0. So we know those, and we have some equations that solve this for us. We know that if we're dealing in 1D flow, then we lose this term because there's no transverse dispersion, because in the y direction all the concentrations are the same everywhere you look, because it's kind of a one-dimensional flow system. So we lose this term, and I guess if we have a geometry that looks like this, we have kind of the same behavior, but it's no longer is the concentration in the lateral direction. Concentration gradient in the lateral direction 0, and we'd have something that looks like, I suppose, this. If we had a constant source, and if we had a non-constant source, which is what we also talked about, then we'd have something that looked like the ripple moving downstream in the current. So this is And we talked about solutions for these last time. And this one here, if it's I guess if we drew the contours for this in plan view, these would be different concentrations, and so this would also is the case when dispersion is not equal to 0. It's not a very good curve. And we get that by solving this expression. And we can rely on usually solutions, which if we plot them out, look like this. And so surprisingly enough, these parameters that we define a Peclet number, which is equal to, I guess it's given above, velocity times the length divided by dispersion. And we have a pore volume, which is velocity times time divided by L, I guess. Right? Velocity times time as you go, the time traveled to get to the compliance point. It actually represents filling the core up with one pore volume of fluid. And so by the time that pore volume arrives at the end, it's ready to move the first contaminated stuff down to the end. And we know that these points kind of go through this 50% mark generally. Peclet number of infinity is vertical, 100 is canted over, 10 is canted over, but then all of a sudden the intercept is no longer at this one pore volume, and we know that. And so we talked about that last time. So you can use these to do calculations. And one of the test questions is about this. I don't know if it's this year. It's either this year or last year. And so if it's last year, it won't be this year, I guess. So using these kinds of curves. And so we talked about those. I guess I haven't played with this recent. Whoops, I didn't mean to do that. Dropping your phone. Does that mean you're looking at it?
She wasn't looking.
What?
I was looking at it.
I'm just feeling a bit chirpy today. Did that open? Not open yet. Fine. So let's see if I can find. Looking for something on my desktop, but I don't see it. So I'll go somewhere else. I can see into my soul when I do this. I can barely see that, but I know it should work. So this is, well, you may recognize it. It has complementary error function in terms of, well, it's this equation here. Oh, that's bad news. It doesn't let you do that. We talked about some closed form solutions to these expressions last time. We didn't look at what they looked like, but they look like complicated equations, and they give us this behavior. If you plot those in terms of the residence time distribution, and you put a Peclet number in of 1, then I don't know if I can, you can see the result here. So this is the residence time distribution. So this is pore volumes on the right-hand side. So can I make it larger? Yes, I can. Whoops, I'm messing it up. So this is one pore volume, and so if we put a big number for Peclet number, 100 maybe, 1,000. Doesn't work with 1,000, doesn't like it. You see that this is the concentration. This is Peclet pore volumes, or number of pore volumes. Did I say Peclet number? I didn't mean that. So when one pore volume breaks through, it breaks through at 50% concentration. Already earlier than that, it's broken through at a lower concentration because of diffusion about the front. And it goes past because some of that concentration has arrived ahead of the front, some of it behind the front is depleted. And I guess it's looking at like these, exactly like this curve that we drew today. The fact that here is depleted and here is enriched, so it's arriving ahead of the front, so it arrives here. That the signal for that is this early arrival, so that when it arrives at 50%, it's already had some stuff arrive before it. And because this concentration is depleted in diffusing ahead of the front, the stuff that diffuses ahead of the front has to come from somewhere, and it's from this mass that would be here, then this is the trailing part that's present here. So that's the part that's there. And so I think if you want, maybe we can use these numbers. Yeah, you see it change shape. I guess that's not so. It becomes strange if the number's small. If we get to 0.01, then you see kind of really strange behavior. And so if this is number of pore volumes, then this is when one pore volume is washed through. It means that it's arrived even though essentially no pore volumes have come through. And so that would represent the case where the advective velocity is 0. And so advection isn't a process, but it's traveling by diffusion, which is not controlled by velocity. And so it arrives infinitely quickly, although it's not really infinitely quickly, it's just saying it's arrived before any pore volume has arrived, which happens at time infinity because it's not flowing. So anyway, so that's equatio. So just to show you that you can calculate these things very readily. So we talked about the individual expressions that would describe these behaviors, and I've kind of drawn them out here. I guess I didn't mean to do that. And so I guess the other thing that might be worthwhile remembering is that these expressions are diffusion plus alpha is a dispersion coefficient times the advective velocity. So this is in units of velocity. This, by definition, is the chemical diffusion coefficient times tortuosity. I think we call it omega d. So this is a term from a small number to 1, which represents for the fact it's going in and out of the pore space. And this is the chemical diffusion. I think we called it dd. And this is a dispersion coefficient. And the units of that are actually in meters. Because together, since this is in meters squared per second, adding apples and apples, they have to be the same thing. We talked last time that this is always a constant and becomes dominant if the velocity is 0. It'll be mainly by diffusion, and if predominantly it's by advection, this term will be small relatively. It won't change, but it'll be very small relative to this term, and so we'd want to know what these terms are that go into this. Transverse dispersion might be a third of the longitudinal dispersion. We kind of saw that because we looked at some results, and this length for our plumes that we looked at was maybe larger than this length. And so since it's conforming, this is the advective velocity, which is only in this direction. We talked last time that Vy advection has to be 0, right? Because it's orthogonal. We're taking the principal velocity, if you like, so orthogonal to that is 0. And so when we do this for the transverse dispersion, this is still d star, and it's still added to alpha transverse, but it's still the advective velocity in the x direction, right? Because otherwise, in the y direction, it'd be zero, and this is zero effect. And so these are the parameters that will define what our curve looks like. And they ultimately end up going into the Peclet number, which is of velocity times a length over dl, and a pore volume, which is a velocity times time over a length. And so, yeah, fine. We talked about what it meant last time. It's essentially a pore volume. Time taken for a pore volume front to get down to the end of the sample, and the length of the compliance point from that. So this would be this. And so I guess I should make the point in representing equatio. Does it exist? When we look at this expression here, if your eyes are good enough, Peclet number is P, X is the T sub R, the pore volumes. And so to get that, that means that we're calculating this concentration at the full length of the core, some length downstream. And so that length downstream is one pore volume for what we used. Actually, these are pore volumes. So this is one pore volume, two pore volumes, etc. So this is just X on that equation. So anyway, so let's talk about how we might measure those parameters. And we can measure in the lab, in the field, by different techniques. Some of them might be useful to us, and some might be of no use whatsoever, and we'll talk about that. So you could think about these behaviors. So if you look at a plume being generated from a source downstream, and you look at it in plan view, then in terms of these coefficients that describe the longitudinal dispersion and the transverse dispersion, depending on the magnitudes of these, we've already said that they might be a factor of 3 different from each other. Then as the ratio of them gets larger, then the shape of the plume is controlled by that in plan view. We could also think of these behaviors in terms of 2-dimensional and 3-dimensional behaviors. So I guess this is kind of a 3-dimensional behavior here. This was along this. And so it's 3-dimensional because we just have something being put into the aquifer right here, and it travels downstream, it widens, and I guess you could imagine that would also deepen in the vertical direction as well. But if you think of this, that you, for instance, would have a source that instead of looking like that was actually applied all the way along this this boundary condition, then the magnitude of the front, instead of looking in plan view like this finite thing, I guess it would just be a series of contours that would represent different concentrations along the width, because really it's a one-dimensional problem. So if you have the same amount of stuff released here, 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 and here, then it's moving down gradient, it's trying to spread laterally, but the piece next door to it is trying to down gradient and spread laterally into it. And so it effectively becomes a one-dimensional problem. Even though it's a 3-dimensional problem, the actual distribution of the spill, if you like, renders it one-dimensional. And so all this is making the point is that in a 3-dimensional system, where it's able to spread laterally because it develops a concentration gradient in the y direction, you'd expect the downstream progression of that plume to be less fast because it's able to spread laterally and kind of dissipate itself, and therefore it won't be forced to travel downstream and have the transverse dispersion suppressed, if you like. And so you might expect that's the case. And so that's the point that's being made here, that if the longitudinal dispersion is, or the transverse dispersion is progressively less and less, then the concentration gets concentrated, so it travels downstream more readily because it can't dissipate itself widthwise. And so it does make a matter as to whether it's a one-dimensional or two-dimensional or three-dimensional geometry. Fine. So if we wanted to measure these parameters, so we want to measure longitudinal dispersion, and we think it's equal to the diffusion coefficient in a porous medium plus this longitudinal dispersivity plus the advective velocity in the x direction. Then what we could do is we could devise an experiment to be able to try and measure what these properties are. And one way to do that would be to take a core, apply on the upstream boundary of that core this concentration boundary condition, just like this, turn it on at time 0, let it propagate along the core, and then measure it at the outlet. Obviously, we can't see in the core to be able to see whether it looks like a sharp front or a diffuse front. We can only look at the output. But if we took the output and tried to fit the output curve of the resonance distribution to this equation, then we could try and figure out exactly what this coefficient is. So, not surprisingly, that's what we could do. And so, what you do is you apply an upstream concentration, you let it propagate along the core, you'd measure the outflow, and you'd plot that outflow in terms of the concentrations when it first arrives, then next arrives, and then you do exactly what we just did with Equatio, I suppose. You could imagine trying to fit the arrival time distribution to the shape of this curve. So you'd know within the core what your advective velocity is because you're applying a flow upstream condition to flush water through it. So you'd know what the advective velocity is, so you could calculate the Peclet number. And by changing and by getting the points along a curve, you could get the best fit through those points. And the best fit through those points would give you a Peclet number. And that Peclet number, if you have it, would give you a velocity times a length over d sub L. If you know the advective velocity because you're putting water through it, if you know how long your core is because that's where you're measuring the behavior, down at the bottom end of it, length, you know this. You know the best fit curve is for Peclet number 10, and so you know everything to be able to calculate that. And so from that, you therefore have this. And if you know your advective velocity down here, you can determine whether diffusion is dominating the behavior or mechanical dispersion is dominating the behavior. And so you can pull that out. And so that seems fine. You could use the simpler version of the curve. So I guess this is just explaining that process. So it's fine, but it turns out that it gives you a good result if you're trying to get diffusion, because that is represented by the slow diffusive behavior in the system. But it turns out to be terrible if you're trying to get this mechanical dispersion term. And the reason for that, I guess you might guess, is that we drew a little figure. I guess it's actually here. We made the case at the end of last time. But one of the reasons why you get a bad result, I thought it was here. Yeah, kind of here, but I'll draw it again. One of the reasons you get a bad result for mechanical dispersion is that if you think about having a core that has a whole bunch of fast flow paths in it, some stringers that are going at a high velocity, then you might expect that the front of your system as it goes through here actually takes the opportunity to travel downstream faster in the regions where it has higher permeability. And so if you take a section across here and you measure the average concentration that is arriving due to this concentration plus this concentration plus this, plus a whole bunch of other ones which are just plain water, then the relative concentration at this point is going to exactly represent the behavior that you have this. It would look like this, I guess, right? So this would be this. This would be this. So upstream it would be 100% concentration because this is what's arriving here. Downstream, ahead of these stringers, it would be 0% concentration. So this is C over C0, 1. And in between it, if in aggregate, at least if you take multiple lines across here and just do the weighted averages of the concentrations, you have values which are in here. And so if you happen to be measuring this at a given location, could be partway along the core, and you're then drawing the residence time distribution that would look like this, where this is time, this is space, this is C over C0, then I guess you'd end up with this between these, right? These would just be the data points that you get from sampling it either at the end of the core or just for argument's sake in the core where the plume moves past it with different times. And so it works well in the case where this is the dominant behavior, but it doesn't work very well when dispersion is dominant behavior because the core is too small. The core is the size of your fist maybe, and so if you want that to represent an aquifer where these stringers might be on the order of a meter or 10 meters or 100 meters in a real aquifer, then it's not really replicating behavior. So doing things like this works well if you want to get the value of diffusion coefficient. It's what we call D star, but not alpha L, because it doesn't have the structure in the core that would lend itself to that. So that suggests that if you can't get good results from a core because of the scale, then you should do something that maybe works at field scale. And so one thing that you could do is if you have a sampling hole, like in your assignment here for the Smithville site, which you can find online if you look it up, if you Google it, and if you have some boreholes in it that penetrate it to do some sampling, what you could do is you could try and artificially measure the values of this longitudinal dispersion by running an experiment which kind of exercises it. So in this experiment, you tried to exercise it by running fluid along the length of it. That fluid was running at some advective velocity in the x direction VA, and you knew that then if you solved the set of equations that represent advection dispersion, you could come back and you could solve for the dispersion that would occur in this. So you could do that in a different geometry, where the influent geometry that you do here is you just pump water with some concentration into it starting at time 0. So you'd expect if you had plug flow that front would slowly radiate outwards from it to being some radius away from it at time 0. So I suppose you could think about, let's see, what would it be? This would be time. So this would be volumetric flow rate, Q, that you inject in. You could imagine that at some time 0, you start pumping in, and then at some time in the future you stop, and then maybe you start pumping out again. So this is adding fluid into your aquifer, subtracting fluid out of it. And I suppose you could expect that the trace that you'd get if you did that might look like what in terms of concentration without going to the equations. So this would be time. This would be C over C0. Goes in, so at time T0, pump in. This is T1, T2. So if you then stop pumping, so this is then T1, T0, and you can only measure the behavior at the well bore. So you're measuring C over C0 and trying to figure what it is. Well, you've pumped it in for time T1, so it's now gone out to here. Now if you suck the water back out, then the concentric circles will diminish as it comes back. So I suppose you'd measure the same concentration until you get to T2, which is here. And that potentially doesn't tell you anything, except it tells you that it's gone out some length and then comes back in an ideal world. But if you have dispersion, I suppose, then probably you'd expect that on this return term, what would it do? It would do something like this, right? So this one here, which isn't red, would be that the dispersion is 0. And this would be that the longitudinal dispersion is greater than 0. It's greater than 0. And the more it gets canted over, the larger the magnitude of dispersion. And so even without these expressions, which just give you the volume that's injected and the volume that's produced, right, which is really just all this is doing. This is the rate of injection, this is the rate that's produced, this is the volume that's injected would be the integration under this whole curve, and this would be the volume that's produced. That if you get the concentration changing with time, then you can use that to solve for the magnitude of the longitudinal dispersion. And so, again, that's not rocket science. And so just getting that geometry would allow you to do that. And that also doesn't give you a very good solution. And the reason it doesn't give you a very good solution is that we think that the longitudinal dispersion is equal to the diffusive part plus this term multiplied by the advective velocity. I guess this would be radial velocity. And so it's a function of this velocity. And so it turns out that the magnitude of these are strongly controlled by the rate at which you inject. So if you inject at a rate which isn't really the natural gradient in the system, then you tend to get a result from this mechanical dispersion which is much larger than reality. And correcting even for the magnitude of the velocity that you're using doesn't really correct for that. And so that's one effect. The other effect that doesn't allow you to get a very good result for this longitudinal dispersion is because it has maybe what we could call geometric dispersion. So if you think, instead of doing, it's much clearer, I guess. So if you look at the flow regime here, and you flow out to this outer boundary, then if you have two particles of water that are right next door to each other, they'll start very close, but they will spread as they get further out. And so you get this spreading, which is apparent here, which if you think about it in this geometry, say you wanted to do an experiment with two well bores, where you inject at the upstream one and you produce at the downstream one. You know how to get the volumetric flow rates through this, right? Through flow nets. So you could calculate the volumetric flow rate in this is equal to number of flow channels divided by the number of drops multiplied by hydraulic conductivity times the head drop, if you remember that. So the number of flow channels is 1, 2, 3, 4, 5, 6, 7, 8. Number of drops is 1, 2, 3, 4, 5, 6, 7, 8. Roughly 1. And you'd get a reasonable value of this. You can also calculate from this, if you have volumetric flow rate, you know that that's equal to a velocity divided by a cross-sectional area. And the cross-sectional area for each of these stream tubes, I guess, would be this area here. And so if you think about the flow through this system, I'm going to ask you a question. Which is the fastest flow tube? This one? First arrival. Has to be this one, right? Gradient between here, this goes to infinity, to the end of the world, and then comes back on this side. It has to be longest. Yeah, just by intuition, you suspect that the ones that has the most direct path as the crow flies between upstream and downstream will be that. And so if this is the fastest one, and these are progressively slower and slower, then I guess you could think about this as being your stream tube, which is kind of like a core. And it's going at some advective velocity from upstream to downstream. And so velocity is equal to length over time. So the arrival time would be equal to length over velocity. So if this is a short length and a large velocity, then this will be the shortest time to arrive. So if you thought about drawing the resistance time distribution at the downstream well, this would be C over C0. Then this one would arrive first, so this is time 0, this is the first arrival. So you can imagine the first stream tube arriving at some time, which you get by this. You know the stream tube next to it, this one, is both longer and a lower velocity, so it will arrive later. And so you'd expect the mass due to that to arrive some later time. The next one coming this way would go, that's not a bad curve, would be this. And those would arrive. So I guess even if you think about the travel in each of these stream tubes, if the travel within each stream tube was actually plug flow with no dispersion, you'd expect it to look like maybe this, halfway along. So if each of these stream tubes looked like this, and therefore dispersion was actually equal to 0, as we'd expect in the advection dispersion equation, the residence time distribution curve that you get still has some dispersion in it, even though there's no dispersion in the system. And it's merely because of the geometry of the flow means that the first arrivals that get there directly come in at only part of the concentration, while these other ones are still bringing in clean water without any concentration. So that's what I mean by geometric dispersion. And so the bad thing about using an experiment like this is that if you have no dispersion, it's going to tell you that the aquifer has some dispersion. And so if it's going to lie to you, even in the perfect case where you have a perfect plug flow, and tell you to have dispersion, then when you do have dispersion, then it's going to accentuate it and make it even more pronounced. And so the bottom line is the result that you get out of that won't be very representative of your aquifer. So we could talk about the equations that give you the arrival time based on these stream tube results and based on the azimuth angle that it comes off at, which is this term here. But I'm not sure that we would necessarily use it. And this is just to make the point that even if it's plug flow, the curve that you get has some dispersion in it for the arrivals. And so you can't use it reliably to get the magnitude of this coefficient that you'd like to get, this dispersion coefficient. So what do we do? So the last possibility we have, so we've talked about the laboratory. We've talked about in the field for single well and twin well tests at what we would call forced gradients. So these are what we would call forced gradients. So in other words, we're making the flow water go through at some rate, and we're driving it by the pressure gradient that we're putting on it. So these refer really, I guess, to the pressure gradient or the head gradient, not the concentration gradient. This is driving flow at some artificially elevated velocity. So what we could do is we could use a natural gradient experiment. And so I scribbled on this last time, so I'm going to take these scribbles off. And so what we could do is we could do an experiment like this, and we talked about it. And so what did we say? We said that if we solve the advection dispersion equation, we end up with a plume that looks like that, fantastic, where this length here is one standard deviation, I guess. We drew this on edge to look like this. This is concentration. This was longitudinal dimension. This was one standard deviation. We call that sigma x. And I think, or we call it 3 standard deviations, I guess, actually, wasn't it? And we said that 3 standard deviations is equal to 3 times square root this is our expression. So I wrote it there. I think it's right. I should probably check. Can't guarantee anything's correct these days. That was this, right? 3 times, not cube root, 2 times dispersion coefficient times time. We can do it in the x direction. We can do it in the y direction. So x would represent longitudinal, y would represent transverse, and the other z would represent the other transverse. And so what we could do if we have an experimental result like this, I guess we talked about it, we could figure out exactly what the value of dl would be equal to. And we do it quite straightforwardly by just using, we know that the advective velocity is equal to the length traveled divided by the time. We know, therefore, that we can, if we have the length traveled and how long it's taken to get there, we can calculate what that is. And so if we know when we start the experiment or when the spill was at time 0, and we know how far it's gone in 647 days, 61 meters, then we have the advective velocity just dividing 61 by 467 days, which comes out to about 1/10 of a meter per day. So we also talked last time about how the fact that we need to know what the advective velocity would be by perhaps getting it also from looking at knowing what the behavior is of the aquifer. So before this has gone anywhere, we have no idea of what the advective velocity is unless we have the hydraulic conductivity, which we could measure, divide by the porosity, and if we can measure the gradient in the aquifer, then we can get the value of the advective velocity. And also, not so different from your other assignments, if you know that the gradient, the contours of the head were 0.1 meter deep and 0.2 meters deep, then this would be not a very good perspective. This would be some length. Then dx would just equal 0.1 meter over whatever that length would be, right? Easy to do. So if you measured the head drop in one direction and measured it in the orthogonal direction, presumably in the orthogonal direction there is no head drop, so you'd have this. So you have the ability to get advective velocity. That allows you to go and look in the right direction at least, so you'd look along this trajectory and then stick your monitoring holes into the ground to be able to pick this up. And so you'd need to know the right place to look. And you'd be able to, so you can use either this or where you locate your plume to represent your advective velocity. We know that we can use 3 standard deviations to represent this. So if we measure this length and we know time, we could use that to calculate dispersivity. So we can get this, we can measure when it is, and so 3 standard deviations for this one after 85 days would be this length here. And so this length here looks like it's about 5 meters, right? This length. So that's this. It occurs after 85 days, so that's this. And so if we substitute that into here, we get a dispersivity of equal to about 2 100ths meters squared per day. Not SI units, but convenient units. If we do the same for this, after 462 days, the longitudinal 3 standard deviations would be equal to about 10 meters, I guess. 14 meters, I guess I've written down here. Doesn't look like, I guess, depends where you take the center of mass. This is the one here, right? This is the outline. So I suppose, maybe it's here. Looks closer to maybe 12 meters. I'm just judging it relative to this. So if this after 462 days, and we end up with similar magnitude of dispersivity, we do it for the furthest traveling one, and it ends up being the longitudinal length is 15 meters and so many days. And they average out at about 0.02 meters squared per day. Not SI units, but we can choose that. We can do the same thing for the transverse dispersivity. This would be d sub L, d sub T. And the same equation is used for that. Be this. It's getting too fancy here. Where the only things which I guess would change would be this. And I don't know what these lengths are, but this is probably about 5 meters, right? They're written down here. Yeah. 4.5 meters, 6 meters, and 6.5 meters. And so what they give, these indeed give you what you now already know. So this is 0.007 versus 0.002. So 3 times 7 is about 21. So it's roughly a third of the magnitude, as we mentioned earlier on. And so that gives us one way of being able to pull out of this very straightforwardly from an introduced source, being able to monitor how it goes downrange, how it spreads both longitudinally and transversely as it goes downrange, and pull out these values. And so if we know what these are, and then we can, actually what we've calculated, I suppose, we've calculated this being equal to this plus alpha L V advective. So now we have this value, which we've just calculated for each of these, here and here, for the two different values. We know what the magnitude of the advective velocity is, either from this calculation here and using this, or by measuring this length here in a given time, which is the same result. So we have a value of this. And so we can calculate whether this is really controlled. Typically, this would be small. In this particular aquifer, it's a sand aquifer with big velocities, and this will always be a constant magnitude. And we said before that this value should be of the order of 10 to the minus 9-ish meters squared per second. I don't know what that is in terms of days. What are we getting? We're getting 2 times 10 to the minus 2 meters squared per day. How many seconds in a day? Oh, he's good. I was going to say 10 to the 5, but it is 86,000. So, actually, I don't like that. That math's too difficult, Sean, for me. Just a simple guy. So that's 2 times 10 to the 3 meters squared a second. And so the only point of doing that is that this is a big number compared to a small number. So clearly diffusion isn't the only effect that we're seeing. It's probably a trivial effect. And so mainly it's due to this mechanical dispersion effect. And so we've recovered that value from it. And so that's it. I think that's all I was going to say today. That was the figure I was looking at. So we understand something about diffusion and dispersion. We know that in any aquifer where we have fluid going at zero velocity, diffusion will be important. And if we look at, say, the residence time distribution, instead of in terms of pore volumes, the residence time distribution would give us something in a diffusing system that would look like this. Knuckle cracker. Why do people do that? Feels good? I've never been able to do it. Never tried doing it. I think I'd break my knuckles if I did it this time. Not a criticism, just an observation.
Your whole life you never cracked your knuckles.
I don't think so. How'd you do it? This?
I do like each individual knuckle.
Is there anyone else who's never done that?
I feel like everybody.
Okay, I guess I'm abnormal, but you knew that. So this is the break, but we digress. So this is the breakthrough point for one pore volume. You know if it's diffusing, it will arrive before those pore volumes arrive. And you know why because of this explanation here. The punchline is that you can get this value of longitudinal dispersion coefficient merely by doing what we just did here for Borden. So you take a whole bunch of locations where you have perhaps natural plumes developing from some event, and you can see how far downrange it's gone, either as a Gaussian distribution like this, or if it was a constant input, you know that the distribution as it goes downrange would look like this, right? This is for a constant upstream source, and it just gets longer and longer as you go down. So you could imagine going to lots of places where you have these observations and calculate from them the magnitude of dl and use that to calculate the coefficient that goes into that, alpha L. And then if you plotted those, very clever plot, relative to how big the plume is. So at Borden, how long was the plume? It's 60 meters down. So the length of the plume is at Borden would come in here, I guess. And so one of these results might be the dispersivity that you calculate for that. But if you do it for this shotgun blast of a whole bunch of different sites at different lengths, you get a whole bunch of data. And if you try and draw the best fit line between these data, you get a value of this longitude and dispersion coefficient is about equal to the length of the plume divided by 10. Which is exactly what this is. This is 0.1 times alpha L. And so that means that you can immediately get the value of dispersion coefficient from using that, right? You know that dl is equal to d star, which we think is small, plus alpha L times the advective velocity. If you know what this is, and you know now that this is equal to this, then immediately you can calculate what this is. Two caveats, I suppose. One caveat is that there's a big spread on this. So if you look at the range of these values, either by looking at this span here, or just do it across for a single site. So this spans, if you go over here, you might have a single value, which is a value of, 70 here? But it spans 1 order of magnitude, 2 orders of magnitude, probably 3 orders of magnitude. So this span is a factor of times 1,000. So although it's a nice way to get a single number out of it, it's not exactly confined to a small range necessarily, because it has some variability attached to it. And so we could be aware of that. And I guess why doesn't it have any physical property attached to it except for the length of the plume? Seems curious to me. Thoughts? You agree? Yeah, you agree. Yeah. So porous media are often thought to be fractal. And so, so you know that a surface that is fractal might have a rough surface like this. If you double the scale of this, then the height of this roughness changes. And so the idea is that as your plume gets larger and larger, it samples a larger and larger volume, and so the chance of having a really big fault or fracture in it, which has a really high conductivity and therefore is doing essentially this, becomes larger and larger. Makes perfect sense. So you take a bigger sample, you have a bigger chance of having a superconductor in it, and that superconductor has a chance of spreading out the plume much more. Then you go to the next step, 10 times bigger. That sample, if the plume is that large, all of a sudden has a really big fault in it, and that has the chance to spread it out larger and larger. And so this is the behavior that you'd expect, that at increasing sizes of the plume, you expect it's sampling a bigger volume of the aquifer, the chances of having a big conductor in that bigger volume are larger, and therefore you'd expect that this coefficient grows. So that's it. Good. No, can't crack my nails. Knuckles. What else should we talk about? Nothing. Good. What does bloop mean? What does bloop mean?
The blue loop,
Blue loop?
bus of loop and the loop. The
What?
catbusters,
Oh, blue loop.
like the blue
Fine.
loop.
No, I never take them. So those buses, can you ride for free on campus, or do you have to have
Yeah, there's.
with an ID?
Right.
Just
Don't
get
need
on.
an ID.
Fine. Should do that. Good. That's all I got to say. Yeah, I don't know. So if we finished what we'll talk about in terms of advection dispersion equations. We've always assumed conservative transport. Conservative transport means that if you put a certain amount of mass in the liquid and leave it there, then when it arrives downstream, it'll always have that same amount of mass in it. And the idea of that was kind of when I mentioned that if we look at these, did I draw it here? Didn't draw it. If we look at the distributions of the mass, the area under these curves represents the amount of mass that's in the system. And so if the same amount of mass is present in the water but just spreads out at a lower concentration, then you'd think that the areas of these distributions would be the same whether upstream or downstream. That assumes that the same amount of mass stays in solution, but it's flowing past porous media, so it may get pulled out of the fluid and attached by sorption onto the porous medium, and if that's the case, then you'd expect that this area under the curve would decrease if that happens. And so what we'll talk about now is non-conservative transport, and the mechanisms that do that are, or the consequences of it being pulled out of the water and stuck onto the static grains are retardation and attenuation. It arrives later downstream because it's been stuck on the grains and it's taken out of the flow field, and it arrives downstream potentially at a lower concentration as the height of that Gaussian peak diminishes, because again it's been stuck onto the solid material, which keeps it upstream even as the water's gone downstream. So that's what we'll talk about next time. Great.